You're moving right now, 30 kilometers per second, around something 150 million kilometers away. You've been doing this your entire life. Your parents did it, every ancestor you've ever had, every human who ever lived, every creature that has ever walked the earth. All of us, along with 7 other planets, dozens of moons, and billions of asteroids, moving in vast, patient orbits around the same brilliant center. At that center sits a yellow dwarf star, 330,000 times the mass of the Earth. And for most of human history, we didn't truly understand what it was tonight. We're tracing the story of the sun, the blinding center of everything we know, the beating heart of our solar system. Let's begin. For thousands of years, people looked up and saw the sun as a god, a perfect golden disk crossing the sky. Bright, warm, life-giving, but just a disk. By the early 1900s, we understood what it was, a star. A nuclear furnace, vast, with us orbiting on a nearly circular path, just at the right distance for liquid water to exist. We assumed it was stable, a constant, unchanging source of light, but we thought it was just burning gas. Nothing special. The problem was visibility. While the sun is incredibly bright, looking directly at it blocks our ability to see its structure. When you look toward the sun with a normal telescope, you risk blindness, seeing only a blazing sphere for centuries. The true nature of our own star was hidden. Then, in the mid-1900s, space probes and specialized instruments began scanning the solar surface. They beamed past the blinding glare, and they found something strange. A chaotic magnetic nightmare. Powerful looping plasma fields. Violent, concentrated flares, too dynamic to be a simple fire, too complex to be a quiet ball of gas. They named the various features, prominences, sunspots, coronal mass ejections. Something incredibly powerful was happening there. Something invisible to the naked eye shaping space weather across the entire system. But you can't see magnetic fields directly. You can only see what they do to the plasma. In the 1990s, space agencies began some of the most patient monitoring programs in the history of science. The SOHO spacecraft, and later the Solar Dynamics Observatory, were both aimed at the same object, the sun. Using ultraviolet cameras, watching in wavelengths our eyes can't register, they tracked individual loops of plasma near the solar surface, not for days but for decades, year after year, image after image, watching them shift, and the plasma moved fast. Not the quiet drift you'd expect from a distant light source. These magnetic arches were whipping around the solar atmosphere, snapping and releasing energy like rubber bands. Far more extreme than anyone expected. Tight loops, twisting, violent. One cycle became the key. An 11-year cycle of magnetic reversal. Unremarkable if you only look at one day, but revolutionary when seen over time. This solar cycle would prove how dynamic our star really is. The sun reverses its magnetic poles every 11 years. That's extraordinarily fast for an entire star. At solar maximum, the point where the magnetic field is most tangled, the sun erupts with flares and coronal mass ejections. Earth, sitting 150 million kilometers away, gets struck by the solar wind. We are close enough to feel the effects of a living star. And during these solar storms, particles accelerate to about 2 to 3% the speed of light, fast enough to cross the distance from the sun to Earth in a matter of tens of minutes. Scientists followed the sun for decades, tracking its activity cycle after cycle. They watched the solar minimum in 2008 and the peak in 2014. One full cycle from quiet to active, and the next cycle is already underway. Frame by frame, year by year. They could see the magnetic fields tighten as activity approached its peak. They could see them simplify as the cycle reset. The path was perfect and predictable. Exactly what you expect from a dynamo operating inside a massive fluid sphere. And they did the math. To generate magnetic fields that intense in a sphere of that size, there has to be an incredibly massive convective zone at the core, crushing hydrogen into helium under immense pressure and temperature. The numbers were precise. Roughly 15 million degrees Celsius at the core, no solid object could survive that heat. No normal chemical reaction could sustain that energy output for billions of years. Only one thing fit the evidence: nuclear fusion. By the mid-20th century, the case was closed. The sun wasn't just a ball of fire. It was a fusion reactor. Our star, for decades, we knew it was there. We could measure its mass, track planets orbiting it, map its gravity, but we'd never seen its outer atmosphere, the corona, in high detail. In 2018, the Parker Solar Probe was launched to touch the sun, flying closer to the solar surface than any spacecraft before. A heat-shielded messenger. Proof. And then, the probe began transmitting data from deep within the corona. This time, closer than ever, it took decades of engineering, because the solar environment is incredibly difficult to survive. Spacecraft must endure extreme heat and radiation. The solar wind is turbulent and unpredictable. It changes constantly, like trying to study a storm while standing inside it, while also managing communications across millions of kilometers. But teams synchronize data from space probes and ground observatories working together, combining signals, compensating for orbital motion, building a picture of our star pixel by pixel. And then they had it. A detailed view of solar wind acceleration, magnetic switchbacks, and the chaotic boundary where the sun's atmosphere ends and interstellar space begins. For the first time, we saw the true dynamics of the thing we've been orbiting our entire lives. And here's the strange part. The sun is not an active supergiant. It's not a supernova waiting to happen. Most of the time, it's relatively stable, mid-aged, a giant working with steady efficiency, which means we're looking at something more reliable than a cosmic explosion. We're looking at a stable yellow dwarf at the peak of its life. And seeing it made us ask, what are we actually looking at? What does one solar mass really mean? One solar mass. That's 330,000 Earths compressed into a sphere 1.4 million kilometers wide. Let's put that in context. If you could somehow hollow out the sun, you could fit 1.3 million Earths inside it. It holds 99.8% of all the matter in the entire solar system. The gravity at the surface of the sun is about 28 times that of Earth. If you could stand on it, you would weigh nearly 2 tons. Now imagine that immense gravitational pull holding distant worlds like Neptune and Pluto in their orbits, billions of kilometers away. The sun's core is so dense that light created there takes over 100,000 years just to escape to the surface, bouncing through dense layers of plasma. Once it reaches the boundary, the photosphere, escape, stops being a struggle from there. Moving at 300,000 kilometers per second, the light crosses the vast distance to Earth in about 8 minutes and 20 seconds. That's the transit, the journey of life-giving energy. And it's worth saying out loud. The sun's boundary isn't a solid surface. It's a horizon of light, where the gas becomes transparent. Inside it, our everyday ideas of matter break down into plasma, a state where atoms are stripped of their electrons and slide past each other in superheated currents. And deeper still, at the very center, pressure is so extreme that physics operates on the quantum scale to fuse hydrogen nuclei together. Now if you compare the sun to other stars in the galaxy, its scale becomes humble. The Sun, 1 solar mass. Sirius, the brightest star in our night sky, about 2 solar masses. Betelgeuse, a red supergiant, around 15 solar masses, but large enough to swallow the orbit of Mars if placed in our solar system. Uiscuti, one of the largest known stars, nearly 1,700 times the radius of the Sun by comparison. Our Sun is small, but small is a relative term. 1.3 million Earths, incomprehensible energy produced every second. And the Sun is just 8 light minutes away, the closest star to Earth. When we look at the Sun, we're not seeing it as it is right now. We're seeing it as it was 8 minutes ago. If the Sun were to suddenly stop shining, we wouldn't know for over 8 minutes. We are always watching its immediate past, and the Sun is ancient. It formed from a collapsing molecular cloud 4.6 billion years ago, when the solar system was just dust and gas. It was there when the planets coalesced. It was there when life first appeared in Earth's oceans, when the dinosaurs ruled and died. It will still be there for another 5 billion years, slowly warming, until it eventually expands into a red giant, shedding its outer layers into a beautiful planetary nebula. And it's been doing the same thing the entire time. Shining, warming, holding. Right now, in this present moment, the Sun is active, fusing hydrogen, emitting light. Magnetic fields are twisting. A solar flare might be erupting on the far side. The solar wind is streaming outward in all directions. Something is happening, but we can't see it instantly. The light that would show us the Sun, as it is right now, won't reach Earth for 8 minutes. We are always watching the past, never the present. Everything we know about the Sun, every measurement, every solar storm we detect, is already minutes old by the time it reaches us. And there's no way around it. Light has a speed limit. Information has a speed limit. We are separated from the true present of our star by a brief but unbreakable cosmic delay. What is the Sun like right now? We can't know instantly. But the past is enough to tell us what the Sun does. The Sun holds our entire solar system together by its mass. It sets the rhythm of the planets. It anchors the very center we measure everything from. And in that sense, quietly, relentlessly, it is the bright landmark at the center of our lives. We orbit it at 30 kilometers per second, fast enough to cross the United States in about 2 minutes. One complete orbit takes 365 days a year. Farther out, planets take much longer. Neptune takes 165 Earth years to complete a single journey around the Sun. Closer in, Mercury screams around the Sun in just 88 days. Some comets have been circling the Sun for billions of years on highly eccentric orbits, diving close to the heat before retreating to the freezing dark. Generations of life have come and gone, all sustained by the energy of this single star. The Sun remains steady. It's patient, silent, but absolute. Every planet bends to its gravity. Every trajectory, every orbit shaped by its presence. We are bound to it. The quiet anchor at the center of our world. Right now, in the sky, there is a star. You can see it with your eyes, feel its warmth on your skin. It's there, and you've been circling it your entire life. So have your parents. So has every generation before you. All of us, held by a star we must study through specialized instruments to truly understand the bright heart of the solar system, not the most massive star in the galaxy, not the hottest, but ours. The center of home, patient, bright, inescapable. You're orbiting it right now. You were orbiting it when you were born. You'll be orbiting it when you're gone, always turning, always bound to the light.